Good morning everybody, I am Sushanta Chakravarti again. Today is the second day, third session of the influence line diagrams. So, let us start with the recapitulation of the previous two sessions, that what we have learned. Let me open the PPT files for the session 1 and 2 yesterday, and then we will start our own session. So, this is session day 1, session 1. Can you see the PPT? I hope. So, this was the introduction to influence lines, and then we have defined what is the influence line, what is its difference with the bending moment and shear force diagram, and then how to draw an influence line for different effects. Okay, and how to draw the influence line with different effects. So then we have also shown on the first day that this is the let us go to the actual construction of the influence line diagram for different effects for a beam. We have drawn the influence line for reaction, and we have drawn the influence line for, and also we have understood that how useful is the influence line to determine where is the effect is the maximum, and also to determine the effect at a particular point or section, and then also the load when it is given at a particular anywhere, we can determine both the reactions immediately. Now, influence line for shear force, we have seen we are sitting at a section, we are trying to determine the influence line of the shear force at that particular point. This will be very useful today. Please please understand that this will be very useful, that the shear force at a section. Then we have drawn the diagram like this. Remember this, we will start with this, and then it is the bending moment effect. We have drawn the influence line for bending moment. We have determined how to determine a value of a function at a particular section when the unit load is in different position from the influence line diagram. So, the load will move anywhere, and we will find the effect at a particular section, that is the influence line diagram. So, due to the uniformly distributed load, area under the influence line diagram multiplied by the intensity, that is for the effect of the uniformly distributed load. And we have also proposed the Muller-Breslau principle, stated the Muller-Breslau principle, and then it is very useful to determine the qualitative shape of the influence line diagram. If you remove the effect and then put it back, the deflected shape of that structure, it gives the qualitative shape of the influence line diagram. This is the influence line diagram for the reaction. You release the reaction, put the the action, that is the your reactive force there, and you got the displaced shape of the beam, and that is the influence line diagram for reaction. Now, this is the influence line diagram for shear. If you release the shear capacity of the beam, if you destroy the shear capacity of the beam and then load the beam with the pair of shear forces, you get a shape which is similar to the influence line diagram of the shear force at that particular section. And similarly, for the moment, you destroy the moment capacity by an internal hinge and then apply the moments, and you get the shape of the two rigid bodies connected here like this, and that is the bending moment diagram, the influence line of the bending moment at that section. For a single concentrated load, for a single unit load moving, we could draw the influence line diagram. For a single concentrated load, we could find we could find out the effect, and also if there is a uniformly distributed load, using the influence line diagram, we could immediately determine the effect at a section. So, those seems to be easy because the load was a single load. Now, you must remember that into that diagram there are positive and negative values sometimes, and also even if there are all positive values like the bending moment diagram for the influence line, there are increasing and decreasing slope of the curve, and there are increasing and decreasing magnitudes once you traverse from one point to another. So, it should be actually the influence line diagram, if it is to be used efficiently for practical structures where it will be very complicated in geometry and loading, we must devise methodologies to cater to increased number of loads and also to cater to the uniformly distributed load which is sitting on the structure, spanning over the entire structure or part of it. Those things need to be actually now conceived. So, suppose we have multiple loading, with that. We could have started with two loads, so we have started with 3 loads probably. We will see the example so that you understand the effect of the multiple load. So, once the influence line diagram of a function which is the reaction, bending moments or shear force has been drawn at a point on the structure, say for a beam, the maximum effects caused by a single concentrated live load is easily determined by multiplying the maximum, that is the peak value, taking the due care of the sign, by the magnitude of that single concentrated load. That is well understood. However, if several live concentrated loads are present, it may not be apparent from observation alone the position of such live loads which have the maximum influence. Examples are the wheels of train of vehicles, load from truck or bridges. One thing is clear, that the distance between 2 loads are mostly fixed, almost always it is fixed. So, a train, it has the wheels, and the distance between 2 wheels or multiple wheels is actually constant. That's one point to be noted, but they can be placed anywhere. Now, either a trial and error procedure is used with a few candidate locations, or a method based on functional optimization used. Now, the thing is that I have multiple loads, probably an example, and we will start. So, let us start with the example 1. I have already examined what is the maximum shear at a point on a beam due to a single concentrated load or a unit load. You can say that we have drawn the influence line diagram. We have already examined carefully that at a section, if I have to find out the maximum positive shear or maximum negative shear, I have already the influence line diagram drawn. This is the cursor, right? Yeah. So, now I have already the influence line diagram drawn. I am seeing that this is a negative effect on the left, this is a positive effect on the right. That means, if my unit load or the concentrated load moves, when the load is here, I have a negative shear here, when the load is here, I have a positive shear here. So, if it is a question of a single concentrated load, I have no doubt. If I have multiple loads, carefully examine the influence line diagram for the shear force at C. It has a linear segment, it is monotonically you can say decreasing in magnitude, goes to more minus as you move from left to right, and this actually monotonically and in a straight line it is decreasing in a straight manner in magnitude, positive magnitude. So, now if I have wheel loads which are differing in magnitude, if I have to account for using the superposition principle the sum total effect of all the loads, I am not so sure that if I place the loads in such a way that one or more loads fall into the negative part, and if I am interested about the positive shear, whether I will gain overall or not. The gaining overall means if my wheel load system moves from right to left, it is the quantities goes on increasing as the slope of the curve from right to left is actually increasing. So, that means if I have 2 wheel loads, if I move from here to here and both of them in positive direction, definitely I am going to be gainer. So, definitely my positive shear will be increasing at this section. Please remember, at this section C, the positive shear will increase, but there is a chance by doing so one or more wheel load actually passes the C point and then they go on to the left. Then I have a loss, because now that load will traverse onto the portion of negative shear, and there will be loss of total shear force acting at this section C. Now, the thing is that the trade-off between this loss and the gain when the other loads are moving upward through this curve is to be examined carefully. So, how to examine carefully, that is the question. You cannot conclude immediately that the influence of the shear force will be maximum for this configuration unless you examine carefully these cases. One thing is clear, that I want to place the loads in such a way that one of the load is at the maximum possible positive shear. So, if the question is that the maximum positive shear at C, if it is under consideration, one thing is clear, that I am going to put this loads, one of the loads at least just immediately to the right of it to have the maximum effect. Actually familiar as well as comfortable with the idea of just right and just left, this type of statements in our engineering. Suppose this is a beam. Now, I am considering the shear force at C. So, a load is here, it is suppose P. Let me put it at the hub point, so that I have reaction P by 2 here, I have the reaction P by 2 here. So, now see here, this P by 2 will create a shear force. I hope you also know the effect of the shear force, that it is, suppose there is a cantilever beam, you are loading it. Suppose by it is not correct to say, because it will be subject to bending moment as well as shear forces. I am just examining if this material of the beam is extremely weak in shear, then the way it will try to deform more than the bending is like this. So, the elements will be trying to distort like this, and if the shear, it is extremely strong in shear, but weak in bending, then it will actually try to bend this way. So, this is the effect of the bending and the shear. So, here what is happening, the shear force, I hope that you are comfortable when you are determining. Suppose the question is that what is the shear force acting at this section, suppose it is D, suppose this is A, this is B, this is C and D, or C. Suppose let us consider the shear force at C. What do we do? We sit at this section, look towards our left or right, whatever it is. Suppose for time being you are looking towards its left. So, what this P by 2 force is doing, if it is the action of pure shear, it is trying to distort the beam like this. It is trying to distort, whether it can or other effects I am not examining right now, it is trying to distort like this. Now, if you cross this if this section is under consideration, sitting at this section, you do not actually touch this section and then consider it. And also there is one more thing. So, this is what is for the left hand shear and the right hand shear. Also consider this force. This will be very interesting to you, because you already know the shear force diagram. This is P by 2, it comes down by P total. So, this is P by 2, it is a positive shear according to us. So, if we consider the VD, then what is happening here, if up to here you see you are coming from left. So, P by 2, P by 2, P by 2, always the shear is P by 2 here, you have drawn the diagram. Once you come to D, if you do not cross the load, you still see P by 2. Once you cross the D point, if you come to the diagram, what you see is the P by load going up and D pushes down. So, by P. So, if the load is P, it is P by 2, P by P down. So, now sitting at a section just at its right, if you look towards left, what will you see is that you have a shear force P by 2 minus B, which is actually minus B. So, you remember your convention left up right down, you have left down. So, according to you have a negative shear force, and that is it. You are, if you are here, you have a negative shear force acting here. So, this is what. So, now the question is that what is the exact shear as D? You have to understand this is you do not discuss it, it jumps from one point to another, and we should not join actually by this line. We should say that the shear up to here is this, and the shear up to here is this, and we do not discuss what exactly is happening here at this point. That our loads, when it is moving from right to left, I have to examine carefully when all the loads are just at this right of this section C, I have all the effects of this load. Now, if one of the load, it's the distance is constant, suppose the whole system is pushed slightly so that this load crosses the C point, then sitting at this section, if I look to my right, the 1 kilonewton load is gone, it has gone to the left part, and I am left out with 2 of the forces. So, that has an enormous jump into the shear force according to our sign convention and the sitting at the section. I think now we can move safely to the actually the example once again. Yes, since the distance between the three loads are fixed, it is not immediately apparent which of the wheel loads needs to be placed directly on the maximum ordinate of the influence line diagram. The compensatory effect, this is very important, the compensatory effect of the negative and positive shear components resulting from the placement of other two wheel loads needs evaluation. Three candidate configurations need to be carefully examined, because we have seen that the maximum effect anyway is occurring when the load is just at the right or left. So, that is the positive and negative effect maximum. So, let us try to do that. So, in the next configuration, see, the first configuration we are examining for the maximum positive shear is you observe that we are trying to determine the maximum positive shear force at C from the influence line diagram of the shear force at that section. So, we have drawn the influence line diagram below it. We know that the net total effect for each load will be accounted for by the load multiplied by the ordinate of the influence line diagram, and by the superposition principle we can add up those three effects. We can sum up all these effects provided we take care of the signs. Now, case 1 is such, again you should be very comfortable that with the statement that the loads are just right to C. So, what is just right? That you have to actually digest, that we are talking about it has not crossed C towards its left, and neither it is exactly onto the C, it is just like take it at, it is a very small distance away. If that is so, then if I sitting at C, if I look towards my right, then I see all the three loads, and as well as it is just right to C means the distance it is away from C is so small that while writing the distance of these two 4 kilonewton loads, I do not account for this small distance. That means, the distance between the wheel loads 1 kilonewton to this 4 kilonewton is 5 meter, and 4 kilonewton to 4 kilonewton again is 5 meters. These distances are not changed by addition of a delta distance, which this 1 kilonewton load is away from C. We compute using the actually the 0 distance from C for 1, but again acknowledging that it is not at 0 distance, it is a very small distance. We neglect that for computation. So, this engineering sense you need to develop, and you need to digest this fallacy, which is not scientifically true you can say, but it is correct in the sense of our computational purpose. Now, case 1, and though these are the difficulties which the students may face actually, that is why we are discussing. Now, case 1 is that the shear force here will be here, if I acknowledge that although I am just right of C, I am computing the value of the ordinate of that point which is just right of C by putting the ordinate at C. So, that is 0.75 here, and similarly this 4 kilonewton is just right of that 5 meter distance, but I am taking the ordinate of 0.625 which is at 5 meter exactly, and this ordinate is 0.5 which is 5 plus 5 10 meters away from this. I have placed this wheel load like this. Now, next is, I am sure that you will be understanding it very well, and this is what is it. Carefully observe that I wanted the effect of this 1 kilonewton load. I have a 0.75 ordinate of the influence line diagram for the shear force at C, which are the values of a unit load when it moves from here to here. What are the shear forces at this point? We have plotted it, and we got 0.75 when the 1 kilonewton load is at C, just right of C. So, the ordinate 0.75. So, 0.75 into 1 plus 0.625 into 4 plus 0.5 into 4. Once again, 0.75, this 1, this 0.625, this 4, this 0.5, this, 4, this. So, you get 5.25 is this kilonewton total effect of the shear for this case 1 when the loading configuration is this. Similarly, you are not sure that now let us discuss about the case 2. You are not sure right now if I push this load system towards its left, if I push this load system towards its left, what happens? This ordinates which were 0.625 and 0.5 onto the positive side of the shear force, they will be definitely go on increasing as I move the system of loads towards the left. But the first thing what happened is that since the 1 kilonewton load was just right of C with a very small distance, if I traverse that small distance, this 1 kilonewton load has actually crossed that C point and it has gone towards its left. It might have fallen down in terms of the influence line diagram to its negative side, and if it has fallen down, it has fallen down from a magnitude of plus 7.5 in influence line diagram to minus 0.25 in the influence line diagram. That is the change of the effect of the 1 kilonewton load at section C. Now what happens if you push it further? You start gaining in terms of these two loads as they are moving towards its left. It is from here to here to here to here to here to here, and this load is from here to here to here to here. So, you are gaining in terms of the positive values as both the ordinates for these loads are kept on increasing, and also for this particular effect of influence line, you are also gaining positively in terms of the negative shear, because it will be from negative 0.25, it will actually increase to negative 0.18 or so. So, that means you are gaining here also, you are gaining here also. So, let us push it. So, how long we will push? As long as the second load which was initially here, it comes just to the right of C. As long as that happens, I will keep on pushing it, and then when it is actually just at the right of C, I have to stop and think that okay, I have more to lose now. I have more to lose now. If I push further, this 4 kilonewton load will actually jump to negativity, and that may be a great loss for me in terms of positive shear. So, I have to pause and think whether this case is optimum or not. Here it is. So, this load I have pushed to an extent that the 4 kilonewton load is just at the right at C. I could not show it in my diagram, neither it is shown in the book. So, it is just at the right of C, and this 4 kilonewton another load is 5 meter away, so no problem. And this 1 kilonewton load which was initially just right at C, it has crossed C, and it was just left of C, and then it moved 5 meters plus something very small. So, I have put it 5 meters. So, it appears to be that 1 kilonewton is at 5 meters and 4 kilonewton is at the top of where the ordinate is maximum for the positive shear, and another 4 kilonewton where the ordinate is improved from 0.5 to 0.65. Here is the calculation. You lost in terms of the first load, which is 1 kilonewton. So, the ordinate here is 0.25 to it has become 0.125. So, this is this here, its position corresponding to this, multiplied by the unit load which is 1 plus 0.75 into this 4 kilonewton which is here. Earlier it was here, now it is here. Now, plus 0.625, what is this 0.625 into 4 kilonewton, that is 5.375 kilonewton. Please observe the changes in the ordinate, 0.75 to 0.125, 0.625 to 0.75 is a gain. This is a tremendous loss, this is a gain, and this is also a gain. Now, these two gain, whether they will balance or overpower the loss, that is to be evaluated numerically, and then only you can tell that whether it is working or not. Yes, see the case 3 then. let us go to case 3. Yes, it is simple. I think I no need to explain so elaborately for this case, because it's apparent that you pushed it towards more to its left, and how much you will push? You will try to push it to an extent where the 4 kilonewton load is still there, the 4 kilonewton load is still there and has not crossed the C point, So, it is still here to contribute positively to the net shear. Yes, it is this 0.75 into 4, it is still contributing positively to the net shear. Now, the other 4 kilonewton has fallen down, crossed, and now it is a magnitude of 0.125 into 4, and this is a gain 0.75 for the third load, but the second load has lost tremendously. The first load has already lost everything. It is sitting on the support, it is contributing to no shear. So, now here is the calculation. 0 is the distance here into 1 kilonewton load, this is the load, and this is 0.125 is this ordinate multiplied by this 4, and this 4 is still contributing positively, which is 0.75 into 4. If it is a question, it was a question of negative shear, probably we could think about that we should cross the last load also to push it hard towards it, so that I can have 2 more ordinates where it will just cross a small distance and it will cross C and sit towards its left. The distance between its just right and just left can also be neglected, and we can see that it is just here, but it is on the left, and I should take the ordinate here in case of there is a negative shear question. So, the negative shear, in case the question was asked what is the negative shear, in this case I should have done 4 into 0.25, 4 into minus 0.125 into 1 into 0 already. So, the difference with this and this is that this could have been changed. This could have been changed to minus 0.25 in case the negative thing is investigated, but for the negative you have to investigate the other cases also, and then you can be sure. So, now you can examine all the cases, that the case 1 and the case 2 and the case 3, you have 5.25 positive shear, 5.375 kilonewton positive shear, and you have a much less positive shear 2.5. So, the absolute maximum at that location, please remember this is the shear force at C. We are talking about C. It is not absolute maximum because we do not know what happens to the other sections. It is an arbitrarily chosen section 2.5 meters from the left, and we are maximum positive shear is 5.375 kilonewton. So, this is what is the case. Now, let us see that the above approach, although accurate, is still a trial and error and may become quite laborious for complicated combinations of wheel loads as well as for complicated geometry of the structures. We must devise a methodology where this examinations, otherwise I have to examine thousands cases, and then I will examine, we will find and evaluate their values for each of them, and then only I can conclude which one is the maximum. That is not possible for practical structures, for complicated loading and complicated geometry. And so, that is why another approach should be devised, which is it can be posed as optimization problem. Optimization, you know, a function should be minimized or maximized with respect to certain variables, and you can take resort to the mathematical gradient based approaches to find out the values where it becomes maximum. It is similar to the Newton-Raphson type of formulation, or you can go for other optimization algorithms like the genetic algorithms and others that you will learn later probably. So, now we are not really discussing the optimization principle. What we are going to do here is that instead of just finding out evaluating the values of the functions, we will examine whether we can determine the slope of the curves of the change, and we can conclude that which one is positively contributing and which one is negatively contributing from the same approach. So, the approach is that as long as the changes remain positive, the new location obviously gives a higher value as compared to that in the previous location. The process is continued until a negative change into the function and the shear is observed, indicating that the previous position was optimum so far. I can explain to you with our example as I have told you. Go to there. If somebody asks me a question that if this 4 kilonewton load is pushed 2 meter, it is pushed just 2 meter, whether, so now suppose it is just pushed 2 meters to the right, I am sure that is going to worsen everything, because in terms of positive shear, because this will go further down, every ordinate will be less than this, nothing has gone out of the span. So, definitely I have something less, but I have to examine all these cases because I was not sure what is the effect of something fallen down to negative, that I had to examine. So, here also the same way we will, the functional changes can be observed, and when we see we are gaining in terms of positive changes, definitely the next computation is better than the previous one. But once we find that I have evaluated something which has gone, the changes is negative, that means definitely it is reducing. So, that is what we will actually now determine. So, I can state the mathematical statements, but I can say the mathematical statements, but it will be more visible if you observe the changes into the function. Now, see that for the same beam problem, yes, for the same beam problem, the changes in shear delta V for a load P that moves positive x1 to x2 over the beam can be determined by multiplying the load P by the change in the ordinate of the influence line. So, that means the changes in the shear delta V, instead of the shear we are talking about, the changes in the shear I can determine by the change in the ordinate multiplied by the P. That is obvious. So, P into y2, P into y1, that is the change in the ordinate, and that is the change in the shear. So, now if we relate, if the slope of the, that indicates the change in the shear. So, in some form. So, the slope of the influence line, if I compute it y2 minus y1 by x2 minus x1, where x2 and x1 are the coordinates of those points, then I can say that the delta V is related to the change, the shear is like this. This is the changes. So, now this is the slope equation. So, I think this is what it is. If there is any discontinuity in the slope, obviously, if it is a continuous function, you can do that, apply the slope formula, but if it is discontinuous function, then the way out is that you can expression for delta V needs to be written directly in terms of the ordinate, or you can keep track of the segment wise difference in the slope. Either way, I have not mentioned here segment wise the slopes, that it can be done also, there is no issue. Now, let us examine what we mean to say. So, for this case, the slope of the this thing, you can say that 0.75 to, so it is, now you put 0 or 0.75, which one, that depends upon you, that it is for the second. So, in which side you are computing the slope, it matters. So, it is 0.75 is the next value, and it is 0 is, it is becoming 0 here. So, I have taken y1 here, y2 here, and corresponding to y1 I have the putting the x1 here, that is why the changes look like this, and so there is no harm, you can form it other way around. So, and positive and negative. So, it is accounting for this slope, and I am going from left to right and then finding out the slopes, that is how it is looking like this. It is absolutely, you take your own formulation, there is no problem. So, it is only thing, remember the decreasing or increasing thing, it is better a decreasing thing associated with a minus sign, and that increasing thing is associated with a positive sign. So, there is no issue, form your own as you are it is convenient for you. Now, let us see that if similarly I have once I have pushed a load and which has fallen down in influence line diagram from a great positive value to a negative value, the jump indicates a great change, and how to account for with the slope which we have already computed and kept ready for that, that is to be actually incorporated into the formula, and obviously it depends upon the particular slope you have here for the diagrams, and this is same here, I think, yes, and that is why it looks like the same. And anyway, now the net change in shear, net increase in shear will be, so in the PPT you have that jump, similarly the jump at C for that load 1 kilonewton which has fallen down is 1. So, plus 1. So, it has that the change is here with the slope, and then you have the slope into the 5 is a distance, isn't it? Then this is the actually the 1 kilonewton load. What it has moved, it has not only fallen down, it has moved. It has not only fallen down, but it has moved by 5 meters. So, it is the effect of the jump, it is the effect of the movement, and then these two has not fallen down in case 1, but they have moved through a slope here to contribute positively more to 5 meter distances, and these are reflected by the distances here, here and here, and the loads here, here and here, here. This accounts for the jump and the loss. This accounts for the gain in terms of as it moves from positive to negative, negative to more negative to less negative. That is why it is positive, and you have the net value of 0.125 kilonewton. Yes, this you just make it a bit bigger. Yes, this portion. Yeah. Now, is handwritten in the class notes I have given to you. You can say that this is the load, this is the jump, this is the load, this is the movement slope, and as well as the length of travel, and this is the length of travels, and this is the slope change in the slope. It is a positive change for the loads from right to left, and these two are the loads themselves. So, this is contributing 0.125 kilonewton positively, and yes, so that is it. So, this is what is happening to the positive changes, and then we will have this delta V this thing. So, similarly, the delta V23 can also be actually computed, and from case 2 and case 3, and now this case you have a jump down for the 4 kilonewton load, which is accounted for this 4 into minus 1, the loss in shear, and this again is the gain onto the negative side to more negative to less negative, and that is why it is positive, and you have the slope multiplied by the distance travelled and multiplied by the load, and for the last 4 kilonewton load you have just gained by moving it from the distance 5 meters with a slope there. And so, this is you have a jump at the 4, you do not have a jump at 1 kilonewton load on the left extreme left that has already fallen down in the last case, and it has only moved by 5 meters, and that is why this is the contribution for the case 2 to 3. So, as you move from case 2 to 3, this is the case. So, you have a negative value, that means the change in the shear now is negative, indicating that as you move from case 2 to case 3, you have lost in terms of the shear force. Now, let us sum up the values. Let us sum up the values. These are the 3 values you have calculated earlier. Now, in between these two, you got positive changes 0.125. Can you just recollect that you already have accounted for that positive 125 in the previous slides, positive 125, and you see that this is negative 2.875, and you see here also in these two cases from case 2 and 3 you have a negative 0.2.875. So, even if that there are two ways, either you evaluate the values of the function clearly there, and you have the value of the functions clearly there, and you have the increments of positive or negative. Once you have an increment from case 2 to 3 negative, you understood that 2 was better in terms of the positive shear. So, you should have stopped computing here, but you did not know, there was no way to avoid the last evaluation of the step. So, you continued with the 3 steps and found out either by evaluating the function or by actually computing the slopes. So, I can show you my computation there in the computation there. So, you 2, 3 you see the class notes. So, this 1 kilometer has moved towards left by 5 meter through a constant slope of this. So, this is the explanation I have put in the class notes. You can see what I have already explained. This is the jump, this is the movement, this is the movement, jump, movement, and these are all movement. This is on the negative side and this is on the positive side. That is how it is computed. So, we are lagging behind in the session purposefully, because we needed a very good and effective and complete discussion about how the shear forces actually are computed, and that is how we will conclude. Now, let us look at here that the maximum bending moment at a point on a beam due to train of loads. I believe by this time you have the basics are clear that what is our approach. I believe that is the thing you have learned through the shear forces, which was somewhat easier for you to grasp. The reaction, which was the first thing we have discussed, it was even easier, but it never gave us the correct interpretation of positive and negative signs. That is why we have not discussed 3 loads cases for a reaction, we have discussed for the shear forces. And for the bending moment, if you see the influence line diagram for the bending moment at a particular section, this is the diagram drawn for the influence line diagram at section C once a unit load actually is moving onto the beam and the changes into the bending moment at this section, all positive. Obviously, there is no change in the curvature and it is always sagging, and this is the positive influence line diagram we have drawn. Wherever you go, you have a positive moment developed at C. That is fine, but still you have a changed slope and you have a changed value. You cannot immediately conclude which one is the best for you, and that is why you need to evaluate either case wise one by one, or you need to have the functions and the slopes properly computed and solve the optimization problem, either way. Now, let us see the first one, that is the arbitrary evaluation of the loads at different locations. Now, this is that what is the case 1. I am not going to explain very detail, because I have already given all details for shear forces. You see, I have placed the loads in such a way that I am this load 2 kilonewton load is just at the right at the section, just at the right at the section, so that I gain maximum here. Now, unlike the shear forces, I do not have a great loss if I just come towards the left. So, it is all the way, if I neglect the just left and just right, I am sitting right on C, and that is why I have the same value of the ordinate here. And here you see 2 kilonewton load and 7.5 is the value of the ordinate, and 4 kilonewton load with the 6.5 of this ordinate, the 3 kilonewton load with the 5 ordinate, and I have 56 kilonewton meter. It should be actually there is a mistake in our PPT. We will actually modify later. So, this is the moment, so kilonewton meter, no problem. Okay. And here in the case 2, you see what should I examine now? I have exhausted here. If I move towards the right, I do not gain anything. It will be only loss, I understand, in terms of positive bending moment. So, now in terms of the case 2, you see, let me try if I have a gain that in terms of because my loads are non-uniform, I have a slightly smaller load as a leading wheel when the system of loads is moving from right to left. So, I am not so sure the loss due to the movement of this 2 kilonewton load towards his left, but the 4 and 3, both these loads will gain in terms of positive moment as it moves into the slope upward in the influence line diagram. So, let me examine the next case by putting the 4 kilonewton load exactly here, unlike the shear force, no just right or just left, just exactly here, and let the 2 kilonewton load fall down here and then wait here. So, like that I can compute the ordinates here, which is 4.5, 7.5 and 6, and I can have the computation 4.5 into 2, 7.5 into 4 and 6 into 3, and that is what I see, that is 57 kilonewton. I gained in terms of the positive bending moment 56 to 57, and check that the delta difference between them is plus 1, I gained. So, I should have gone for the next second case, but I did not know, that is why I have examined both. Now, you see that next case is this. Next case is this, you do yourself, I leave it to you to interpret them. I am not going to give you details. So, this is very easy for you to compute. Mind that one load has gone off the track to the support, directly going to the support, not contributing, I have a very less value and I have a negative changes, and that indicates that I have lost in terms of positive bending moment. I should stop at the second case. If you have any question, you can ask me. If you have no question, you have understood well and perfectly, that also you can convey to us, or whether we need to explain more or everything. So, if you have any questions, 10 minutes we can discuss, and then we can continue with the same session. So, I will wait for your comments over the last proposition of the shear force and the maximum shear force determination. I think these are very, very basic. Once you understood, I guarantee that the rest of the journey will be very, very easy, and you will understand everything. So, let me wait for your comments. So, please comment, even if you have understood well, tell that. If you have not, then also tell that where you were stuck, and we can show it once again, no problem. So, you understood that there is nothing great difficulty to learn. The only thing is that the carefulness with which you should deal with individual problems, and an observational power is required to examine that which are the cases are probable candidates. That is not, there is no theoretical background for that. You need to imagine, there are certain cases need not be examined very clearly. You can eliminate them. It will be extremely difficult when there will be multiple load paths on a structure. There will be wheel loads moving from one direction to the other, and another part the loads are from other directions. Suppose there is a bridge with the trains, the moving in both directions, and at different occasions they are crossing a section with at different times, and that you have to examine carefully, that with the combination of other loads how they behave. It's not easy to find out the cases. It's not easy for complicated structures. You need a well formulated optimization problem. You need to, and if it is a dynamics, we are not doing dynamics. We are taking care of the increase of the loads by some impact factor or something to take care of the dynamical effects. In real dynamics, you have to take care of the mode shapes also, which will be the different positions of the structures due to the load, and it will contribute completely differently if the inertia forces are to be taken into account. So, it is a quite involved and complicated case. We were effects of series of concentrated loads. We have started with the shear, explained with greater detail, and then how to compute the ordinates. It was easy. Ramlal's question is that in case of UDL, how you find out? We will do that. Now, this is the slopes and the arbitrary evaluation, both we have evaluated. We have evaluated the changes and concluded the shear force problem. I have not spent much time for the bending moment problem, that you do yourself, because it is a case study similar to the shear force, and these are the cases. So, if you want the explanatory things, how it is computed, there is no jump here, but loss of slope or change of slope. So, this indicates by 0 minus 7.5 to 7.5 minus 0, which is indicated here with a span of 0 to 10 and 10 to 40. So, this you please see, and I think I have this explanation in the class notes. I can show you once again. Within this, you see the class notes later, everything is explained how it has been changed. I hope you can make it out. Okay, thank you. So, let us go to our point of discussion in this session first. It is continuing from that session. Maximum bending moment at a point on a beam due to uniformly distributed load. There are two cases. One is that the case 1 UDL, uniformly distributed load. It is still uniformly distributed load. I have directly copied from the class notes, and then it is from Professor Hiblar's book anyway. UDL is longer than the span, and something has been taken from NPTEL course IIT KGP material, because the derivation was very concise. That is why I have taken from both. And now, case 1 is UDL is longer than the span. So, the question is that how can the UDL be longer than the span? Why not? Suppose the train is moving, the bridge is only 10 meters. The train is suppose 1 kilometer. So, naturally, the rest of the portion, suppose there is a 10-meter bridge and 1 kilometer long uniformly distributed load, suppose it is moving. Let me treat the train as a continuous uniformly distributed load. So, 1 kilometer minus 10 meter, that rest of the length goes directly to the ground. I have nothing to bother, and that portion of the bridge is always loaded with some part of the uniformly distributed load. That case I am dealing with. If that is the case, if I am sitting at a section of at C, and if I try to find out what is the maximum effect of the bending moment, then I think I already know what is the influence line diagram for the bending moment at C from the reactions due to the unit load, the reactions from the unit load. Mind that this is for the unit load. The influence line diagram is drawn for the unit load, and that's it. And you can it's a span of L I have given, not the 10 meter like before. That's why it is looking like that. Is exactly the same problem, and you can find out the moment at any section due to this. Now the moment which you need to find out is the area under the influence line diagram curve multiplied by the intensity that we have actually discussed in the first chapter. Now let me answer the question of Mr. Namlal. That his question is probably is that can you please explain ordinates for UDL longer than the span and how to find out? Yes. So this is the, so suppose there is a particular span, it is totally under UDL. The UDL is, so this is the span. So this is the span. It is continuing for it's going like this, the UDL, and I am not bothered about this load and this load, this and this is directly going to the ground. I think you need to zoom out. You need to zoom out for it a little bit, and need to zoom out. Yes, now it is all right. So now we are concerned about this load, and this is the influence line diagram for that. I have drawn for the bending moment at a section C, and this is the influence line. I am not giving the ordinate. If your question is related to how to find out the ordinates for this, in fact, if I have told you that it is the area of the influence line diagram, or and also multiplied by the UDL. If you are not satisfied still searching for the ordinate for a UDL in an influence line diagram, divide into several parts and also divide into rectangles by drawing lines here in the from the midpoint, so that this small triangle and this small triangle compensates each other. You will be left out with several rectangles, the area of which will be describing the ordinates, and the midpoint of that is the ordinate of this. So you will be having small rectangle and their ordinates, and you can apply the first formula which is for the concentrated load, and you will get the same answer in the limit if you actually reduce this dx length. That's it. So when you find out the area of a rectangle, you do exactly that. So it is 2 by 3. So it is suppose 2 and this is 3. So the area is this 2 by 3. So now similarly, suppose I have a I have given this thing, that's it, means 2 multiplied by 3, or 3 times adding 2 is actually the same. So that's what is the answer to the queries how to find out the ordinates for the influence line diagram for the uniformly distributed load. Now going to that your this thing. So I have an extremely simple exercise of finding out the area of the influence line diagram multiplied by the UDL, that gives me the actually the bending moment at from the influence line diagram. This is an influence line diagram, not the bending moment diagram. So that gives the influence at that point of the bending moment caused by the UDL at that section. Like that, I can say that if I am at the midspan, I will find from this formula omega L square by 8, and that will convince us that I am on the right track. Okay. So now let us go to the next. A little bit of interest will be when we have the UDL shorter than the span. So it is not entirely the span, and you are having actually a shorter span of the application of the UDL than the span of the structure itself. So the occupancy of that UDL, the uniformly distributed load, where it is placed, that matters a lot for the computation of the effect of the bending moment at C. So if the load is on the left, there will be bending moment obviously here, if it is right, bending moment, but not on the same way, because the reactions will vary, and depending upon the position, also the distance will contribute differently to the net bending moment. So how to find out that? You see, you can find out the reaction, and you can find out the expression for the bending moment at C, and you can well understand the difference. Now there is something to learn about, that a little bit of optimization of the expression for the moment at C in terms of the uniformly distributed load and the y, which is the distance between the end points of the loading, which is y, and this is the center line of the loading, it is actually placed at a distance z from the left end, and you have at a distance x of your section under consideration. There are so many things. Once again, let me explain. What you are doing is that I am examining the effect of a uniformly distributed load, which effect of the uniformly distributed load which is spanning over a length of y, which is less than total length of this twice z, and also it is the section is at a distance x from the left end, and we are examining that what is the condition when we can get the maximum of that. So, a little bit of manipulation of the expression for MC with this. So, what we want to find out, if this is the z distance, which is the center line of the loading. Yes, sorry, the z is the center line of the loading, where the actually it is not a center line of the beam. The z is the center line of the loading, which is y by 2 this side and y by 2 this side. So, the load center is at a distance z from the left end, and it is spanning y by 2 this side and y by 2 this side, and I am examining that what is the effect at a section C, which is at a distance x, and it has been cast as a variable form for MC. Now, if I have to find out what makes this MC an optimum or the this maximum value with respect to the position z, which is the center of this loading. So, I must make the derivative dmc by dz is equal to 0. If I do that, ultimately with lot of manipulation, I will land up into a very, very important conclusion that the bending moment at a section will be maximum when the uniformly distributed load is so placed that the section divides the load in the same ratio as it divides the span. You see, the section divides the load in the same ratio as it divides the span. So, if you go back the section divides the it is the same ratio of the span. So, from here to here and here to here, it will be the load will divide in the same way. So, now if you say that if you go to the if you stick to the diagram, if you see the expression small a c divided by small a capital C divided by capital C b, that means small a is here from here to the section. So, the section has divided the section where you are interested. So, a c divided by c b will be the same ratio is a capital A c and then capital C b. So, the thing is that this divided by this divided by this will be this divided by this. So, that is how it will be having the maximum effect. So, UDL shorter than the span will have the bending moment at the section will be maximum. So, the conclusion ultimately comes like this: the bending moment at the section will be maximum when the uniformly distributed load is so placed that the section divides the load in the same ratio as it divides the span. You can find out like this. It's a once such conclusions are made, a lot of problems will be formulated in different textbooks to exploit this formula, to have different case studies, but I hope that you will remember the basics, and all subsequent problems in different forms can be solved this way. If you have a multiple loading system and your or uniformly distributed loaded system, it is like this. So, now absolute maximum, now and another discussion should immediately follow up. What we have discussed, carefully observe, we have never shifted from this thing that our section under consideration is still so far defined, because in design this is the main thing. The designer is sitting at a section and examining its condition of different stress resultants. That is why we discussed it first, but ultimately I have to resolve the issue that if this section is also changed from different location, how does actually the effect changes. For that, an absolute maximum shear and moment condition need to be actually carefully examined. A more generalized problem involves the determination of both the location of the point in the beam and position of loading, so that one can obtain the absolute maximum shear and bending caused by the loads. The problems described earlier involved computation of the maximum shear and bending moment at a specified location C. Please remember this. We are now going to examine, I do not know where the things will be maximum. Tell me the absolute maximum. I want to sit there and see that it is the maximum value. And what is the maximum value? Generally, the problem is dependent upon the support condition. So, we need to discuss something related to different support conditions. So, suppose now your intuition should tell us the answer. Suppose you have a cantilever beam. A train of load is moving on a cantilever beam. Yes, it can be a part of the bridge. A part of the bridge can be actually cantilever, no problem. A small bridge can be cantilever bridge. So, now where the maximum shear and maximum moment will happen? Now, there is only one support. Now, this loads are moving. So, unless I sit in the middle of that, if I cross these loads, then definitely I will have the contribution of all loads accounted for. So, keeping these loads on one side, wherever I am keeping these loads on one side. If I sit on the just right of this section, I will have the maximum shear force anyway, and obviously the maximum shear force I have to account for at the supports. This is the only support which we have for the cantilever beam. So, the loads can be anywhere, but the shear will be maximum at the support here. Now, it can be the same for different section if the loads are here. So, it does not matter if I am sitting right past all the loads, and the answer is this. So, but for the bending moment I want the maximum effect. So, what I need to do is that I need to place the loads at maximum possible locations from the fixed end to have the maximum effect. Of course, if I have this configuration defined, I cannot change it, means I cannot put the load into my choice of, suppose this is 1 kilonewton, it is 10 kilonewton, this is 100 kilonewton, suppose. Then I will have the maximum effect if I have the opportunity to turn the load around, the 100 kilonewton load is extreme end, then I will have the maximum effect. But if I do not, then I have to accept that I have that 100 kilonewton load here and 1 kilonewton load here. So, like that for the cantilever it is very easy. For the simply supported boundary condition, it is definite the maximum shear will occur when the loads are at the extreme end towards the support, but just passed to the right, pushed to the one end, and it is just towards the right. So, I have the maximum shear sitting here. And next is that so simply supported condition, it is somewhat for even for simply supported condition, the condition for maximum moment cannot be readily determined from the observation. The loading may consist of several concentrated loads. The bending moment diagram for each concentrated load consists of straight line segments with maximum value below the respective loading. Hence, it can be guessed that eventually the maximum effect has to happen below one of the load, but we do not know really that in a combination of load what should be the exact position. I know that it is going to happen below the load, but how to compute that? Let a beam, so this is the condition. So, this is the beam, I have a train of load. Now, I am trying to find out that so this is a beam AB of span twice L carries 3 system of wheel loads at distances D1, D2 and D3. D2 and D2 are the distances between this, okay, D3 is not there, with a distance x, with a distance x. So, this load is placed from the central line of the beam for its central wheel load F2, for its central wheel load F2. I have to examine that what is the absolute maximum effect. If Fr is the resultant force of all the wheel loads and the line of action of this resultant is located, this is the line of action resultant. So, please remember that either you have this resultant force or you have this load system in which are working on the system. They do not exist together. So, this is the resultant force, that is why it is shown in green, and I have this resultant force. Now, I have in the computation, I will just see that what condition it is actually arriving at. So, if this resultant is located at a distance of if this resultant is here, I can find out the resultant, what distance it is having from the center line of the beam, which is at L by 2. So, please once again see that our loads are at a distance d1, d2, 3 loads. This load, the center line, which is the geometric center line of the beam, from there the F2 load is at a distance x. I know that the reaction is acting here, I can find out here. Now, I have to find out the absolute maximum, actually the bending moment, which is not immediately apparent. So, there are certain computations, I think it will be very elaborate to discuss and prove. We will spend a lot of time, but ultimately the conclusion you have to accept. So, it is better to go to the conclusions first and then see. This you can do it in background study from the materials we have given. It is given in any book and you can easily grasp. Let us see the conclusions, what it says. It says the absolute maximum moment. So, it says the absolute maximum bending moment, the absolute maximum bending moment in a simply supported beam occurs under one of the concentrated forces, such that this force is positioned on the beam, so that it and the resultant force of the system are equidistant from the beam's center line. Once again read that. You will arrive at this conclusion that x is equal to x dash by 2, x is equal to x dash by 2. See that, and let me go back to the diagram. So, this is what you have concluded, x is equal to x dash by 2. What is x dash? X dash is from this to this, and what is x? X is from here to the center line. So, basically this distance, which is x dash minus x, is equal to x. So, you can conclude that x is x dash minus 2. So, this two distance, if they are equal, then you can say that your that might be a condition, but you have to examining this for other loads. So, what I mean to say, let me show you with a small piece of paper. So, what should I do? Can I draw this on my pen and I can move it here. So, this is my load system. Let me prepare it first. So, this is my F2, shall I do it here? This is my F1, this is my F2 and this is my F3, and this is the system of loads which are moving. So, let me make a small piece of paper ready for me. This is the load I should have shown properly. So, this is moving and here is the actually the resultant R. If this is the resultant R, I should have it properly. Anyway, once it is moving at a point when this R and this F2 are equidistant from the center line, this gives the maximum effect. This gives the maximum effect. So, if you go this side or this side, that actually the bending moment reduces. So, once this R is placed in such a way that F2 is equidistant, that means here, here. So, this is the distance we have. So, if this is the distance, though I have this is the position when the effect will be maximum. That has been concluded. So, this is the conclusion which has been made without derivation here, because this is the figure we have drawn, this is the midpoint and we are done with. So, the conclusion was this, and this is the interpretation, and I have shown you that how I have moved the load so that its x is becoming x dash by 2. So, I believe that that is it. For the complicated arrangement you will have difficulty. There is a series of concentrated loads and the problem is solved. I will not elaborate much because it is a direct application of this So, I believe that this is you can do it yourself. So, I no need to explain, this is it is taken from Professor Menon's textbook. So, Professor Devdas Menon is a faculty at IIT Madras and from his book I have extracted this problem because it was so good. It clearly explained that what is happening. You see that I have a 120 kilonewton load, I have a 400 kilonewton load, I have a 150 kilonewton load, I have a 250 kilonewton load. I have the resultant of 120 plus 400 plus 150 plus 250, which is 920 kilonewton load. And if you want to find out that what is the actually the CG of that loading, you can easily find out from the computation of I will show you later. Can I show it next slide? Yes, this is to find out at what distance x dash from the left the resultant should be located. So, this is where it is located. If it is located there, you see that I have found out that this is the location x dash, and I have located that where it should be the resultant, the pass through. So, this is the geometric center line, and from the geometric center line now you can have the computation, everything ready. You have the distance between the loads known. A little bit of computation onto the figure will be very good for you. You have already computed that the what you have computed in the formulation, that x is equal to x dash by 2. So, this geometry, this is the center line of that, where 250, so total is 5 meters. So, it is 2.5 meters and 2.5 meters here. So, the red line, from there you have, if you consider that the 400 kilonewton load is creating the maximum, then you place it in such a way that the 400 kilonewton load and the resultant are equidistant from this lead line. That is it. After that, it is a matter of geometry to compute the ordinate of all the actually the influence line diagrams, and then you can find out the maximum effect there. So, and the rest of the thing is the computation. So, I am not going to elaborate, please do the background work. It is purely a geometrical problem once you accepted the fact that you are going to place one of the load equidistant from its resultant. If not, if you do not accept that F2 load is creating the maximum effect, you will place the other load, you will place the 150 load probably, but there is no point in placing the 120 or the 250 loads easily unless they have a very high magnitude. But if there are comparable magnitude, then probably the inner loads will have support from the bending moment of other loads, and we will have the maximum effect. That is why the point of actually the discussion should be with 400 and 150 kilonewton load. So, that is it. Now, we will actually ask you to continue with the 120 kilonewton load, and then you will find it that the ordinates will change and you have a value which is slightly less than this. So, then you can have the maximum moment for both of them. So, let us continue straight away with the influence line diagram for determinate structures for the bridges. So, now I told you in the very beginning that while discussing about the influence line, it can be the beam type of structures, it can be the bridges where the influence line diagrams are mostly used. That is why we have to discuss the beams, we have to discuss the bridge structures itself, we have to discuss the cranes, the floor girders, and also the building frames, etc. We cannot discuss everything. So, we will discuss the truss and building frames and conclude. So, bridge structure is different from the beam in the sense, you know that the trusses, they are basically plain trusses mostly. They are basically plain trusses. Plain trusses are mostly used in the road bridges or railway bridges. Space structures, suppose a space trusses, you will see in airport terminals and others, there are big space trusses many a times. Sometimes there are plain truss too. So, plain truss is most popular. There are two plain trusses on both sides of a bridge connected by the cross beams, and that is or the cross connections they are subjected to. So, now we are concerned about how if a load moves onto the floor, either it is a train or trucks. So, it will be loaded and the stringer beams will be loaded, they will be transfer the loads in through the cross beams which will be across to the node points of the trusses, and that is how they are trusses. They are loaded at the points, and then these truss forces will be purely axial, or the predominant force will be purely axial, and a little bit of moment can be easily taken by the frame action, which we do not take into account. Now, predominantly the structures is subjected to axial tension and compression, as well as due to the movement of the vehicle on the floor, the load is transferred to the node points, which is increasing gradually. So, the discussion is concentrated on bridge trusses first, and the load transfer mechanism is explained through the diagram below that we have done. Now, the cross beams are conveniently placed to connect the trusses on both sides of the bridge. Since the truss member are affected only by the joint loading, the ordinate of the influence line diagram for each member can be obtained by loading each joint along the deck with a unit load and then use the method of joints or method of section for the member forces. So, it may look ridiculous that suddenly we have shifted from loading a structure by wind load by unit load, and it should move on my structure, and then only I will actually examining that what is affecting. We are doing so, but the load transfer mechanism is such that it is moving on the floor, it is not moving on the trusses girder, a trusses bottom cord. The bottom cord is always in tension and compression, it is not taking any bending like the beam. So, I have to evaluate the joint forces which is contributing to the axial tension and compression, and that is through the movement of the load onto the floor. So, it is judicious for me if I load the joint of the truss and if we have the unit load acting there, and I can solve the truss and get the member forces. So, now let me go to the PPT once again. So, now if the member forces are tensile, it is taken as positive, if it is compressive, then it is taken negative. It is obvious. From the relationship between unit load at joint and the member forces, the influence line for particular member is constructed by joining the points by straight line for these statically determinate structures. Once again, we have so far discussed everything for statically determinate structures, and we are discussing for statically determinate trusses. And the influence line diagrams are straight lines, as we have learned earlier, because it's if you release a structure from its support or member forces, it becomes actually it's unstable, and that's how you have the rigid body movement of the parts, and that's how it becomes straight lines. And now next, straight lines. So, now let us take an example of a truss. So, what should I do with the truss? We will examine what are the how the member forces changes as a unit load moves onto the floor, and we have already agreed that what we will effectively do is that ultimately that unit load has to cross the node point, and while crossing the node point it has a unit load. So, let me examine at each of the node points through the load transfer mechanism that the unit load is moving onto the bottom cord, suppose. So, all the points, suppose the unit load is moving at the bottom cord level onto the floor, the unit load is moving onto the floor and at the bottom cord level. So, while it is moving, it will be once here, once here, once here, once here, once here at least, and the in between when it is on the floor, the effect, since it is a linear, we can easily join the effect from here to here and get the effect in between when the load is in between. So, I have to load at each joint, solve the truss. This is a very easy task for you once you have solved it this kind of problem in your first year mechanics. So, I believe that you have remembered the joint equilibrium for the trusses, and you can solve them for the method of joints or the method of sections. By the way, one interesting thing, and also one thing to be remembered, suppose there is a truss and you are trying to solve it by the method of joints. Please remember, what you do is that you actually separate the members of the trusses and the pins So, these are the pins where the members will be connected. You solve actually the pins, not the members really. So, you solve for the members indirectly through the equilibrium of the pins, and a force which is away from the pin, it is taken at tension, because if you say this is the direction of the force away from the pin, equal and opposite forces on the member, and you can imagine this is trying to stretch the member. So, this is tension. So, when you solve by method of joints the pin equilibrium equations, a force which is directed away from the joint is actually in tension, and a force which is towards the pin is actually compressive, because the equal and opposite force will act onto the member, and you can see that they are compressing the member. So, this is in compression. So, method of joints assumes the truss as pin connected, but method of sections, when you take the method of sections, they consider the truss to be a part of rigid body. So, these are the two rigid bodies, and you can solve by the method of sections considering the truss as rigid body. You should not have any difficulty in solution of a truss that we are treating is as rigid body in while doing the method of sections, and pin connected parts, rigid parts, while dealing with the method of your joints, and they are absolutely applicable. If you make several sections of the truss and separate out, both the methods actually effectively technically coincide with the different assumptions. So, this is out of the way discussion, we do not need them. Actually the so this is very easy for you. Once I have loaded with unit load, I have the external reactions, go for the method of joints, go for the method of sections. I have gone for the method of sections, I have cut it. This is one rigid body, another rigid body. You have done it. Any rigid body you cut into two pieces, they will be in equilibrium individually. So, you cut into piece, remove one part, the other part will be in equilibrium with the reactive force, and the part the loading comes from the other part. So, that is what the rigid body equilibrium is. So, equilibrium for this truss will be solved this way, and you have the member forces determined. I am not going to detail because it is very easy for you, and you will solve the member forces due to the unit load elsewhere also. So, this and you can continue with this kind of loading at B and at C, and then continue further at this point, and you can at last tabulate the force into a particular member for which you are drawing the influence line diagram. Once again, as the influence line diagram of shear force and bending moments was at a particular section for the beam, the influence line diagram for the truss is for a particular member. So, it is the particular member force, the influence of the unit load moving you are determining. So, that is the influence line diagram for a truss. So, influence line diagram for the force member FGB. So, it is the force into the member GB of the truss as a unit load moves onto the floor. That is the influence line diagram for the truss. Now, please see that once again the results. So, yes, this is the thing. So, if you are here, it indicates that as the unit load moves, I have the member force of the member GB minus 0.707. That is, it is compressive when the unit load is here onto the floor, and in between, if it is on the floor, I can also determine the effect. So, in between onto the floor, if it is onto the floor here the unit load, I have the effect here, and I can interpolate and determine. This looks very very easy, and since these are straight lines to determine in between effects. We will see it is not that easy for statically indeterminate structures. For the determinate structures, it is. Similarly, all influence line diagrams for the member forces of all the truss members as the unit load moves onto the floor can be drawn very easily by tabulating the values. Of course, this can be done by finding out the gradients, but it is less useful as they are straight lines. Of course, you can do that the change. So, now you can follow. So, application of Muller-Breslau principle to draw the qualitative influence line diagram for the truss. We have already used the Muller-Breslau principle for the beams. We have seen that the effect for which we are drawing the influence line diagram, we can get by actually removing that effect. So, I am interested about the drawing the bending moment diagram in a beam at a particular section. First, let me destroy the capability of the beam to resist bending moment there. How can I do that? I will introduce an internal hinge at that section, so that the section no longer remains actually resistive to the bending moment. So, it will give way for the bending moment, internal hinge. Once that is happening, I will apply a pair of moment there and see that how the section actually is trying to deform, and that was giving my influence line diagram for the beam. Now, coming to the truss, again to the coming to the truss for the you are determining the Muller-Breslau principle for the truss can be stated. Muller-Breslau principle for the beams can also be stated equally well to generate the deflected shape. Okay, this is the description we have not stated. Anyway, so for the truss, since it is not subjected to bending moment shear force, but the axial forces, so the capacity of that particular member to resist that axial force either in tension or compression, I will destroy, and also try to pull it to a certain distance, suppose unit distance, to see that how the configuration is changed for the truss, assuming the sections are pinned at that particular member ends. So, if that is happening, that how a truss is actually deforming and keeping track of the node points, how they are displaced, joining those node points, we will get the shape, qualitative shape of the influence line diagram. We have this. So, let us examining the truss. Let us examine the truss. Where is our GB? So, this is GB. So, this is red mark is GB. This is an inclined member. So, this member with the unit load we have placed at different locations. We have found out the member forces, and we have plot the actually the influence line diagram by plotting different values. It looks like this. Just remember how it looked like. It has gone up here, gone down here, and gone again back to this thing. So, keeping this two as a reference line, we have a small triangle protruding here, another triangle protruding here. Now, let us go to our influence line diagram if we can draw from the Muller-Breslau principle. The Muller-Breslau principle, this the black, this is a hand drawn figure, this is there in the book. Okay. So, now this is the truss. I have hand drawn this from Hibbeler's book and other books also, the same problem is there. So, this black lines are the original trusses, this. Okay. So, these are the original truss members. Now, if I say I am interested about the influence line diagram for the member forces of this member, let me destroy it first. So, I am cutting it the GB member. So, I am cutting the GB member and then trying to pull the both ends of the member either in tension or compression both. So, I am pulled it to make it closer together. So, I am pulling it, the GB member cut and pulled towards each other. If I do that, then you see this particular square, it will give actually this particular square, this particular square will actually become rhombic. So, this particular square, it has become rhombic. So, this is the actually the shape of the rhombus with these members coming closer. By doing so, definitely you can remember that this square, if it becomes rhombus, this point will be going up and this point will be going down. So, keeping track of what is happening to this point, you have now you follow the green portion. This triangle, suppose it is intact, this part I have not drawn it properly, it is hand drawn. So, this triangle and this square should have been intact, with this portion only becoming rhombic instead of square. With that, if you can join these three node points, then this node has gone up and this node has gone down. So, can you see if you join the reference line once again, you can see the shape is just looking like the actually the influence line diagram for the axial force into this member. Yes, probably you can discover this for other members also, and you see that what you need to do is very simple. You wanted the influence line diagram for a particular member forces, destroy it the capacity. So, it will hang and then try to either push it this way or this way to some scale, it will actually display you the shape of the your influence line diagram. This can be done experimentally as well. So, we can do it very well, but it is drawn in a linear scale basis, so that we have not changed the length. So, in fact, unless you give freedom of movement, experimentally it will be very difficult, but if you give freedom of movement here, you can clearly see that the rhombic formation, and this is going up and this going down, and you can have a shadow of this structure replicating the influence line diagram. So, now once again I have drawn it. So, statically indeterminate trusses, I should say that it will not be that easy, because statically indeterminate structures, there won't be rigid body movements like this. It has to bend, and there will be for beam it has to bend, and for trusses there will be other redundant members present which will be further loaded. The load will increase or change, but it will not be relieved to show you immediately the rigid body movements of the parts like this. So, it will be less useful, and the first hand information will be actually equally laborious, or if this also will not be very convenient. Let me have a complete summary of session 3 and 4, and then we will be actually it will be open for discussion and for your comments, and we will discuss. So, this is session 3 today. So, what we started in the morning at 10 o'clock. So, it is day 2 session 3, and you have that effects of the series of concentrated loads. We started with an example of shear. We spent almost 45 minutes so explaining everything. So, I hope now you are familiar with the problem, and these are the effects. You can remember that if you have to examine with different magnitudes of load, do not be sure that it is with a somewhat bigger loads. Your position matters. You are not really in a position to determine readily by observation. You have to do some computation first. Now, it is easily extendable to a format of slope change and the changes in the function instead of the functions themselves, and once the function changes negatively, we are predicting that the previous one was better, that right now it has gone worse. Like that, it has been extended to so I have shown you the computations at last. This is the maximum. It has been extended to bending moments, and these are the cases. So, and it has been also we have discussed about the UDL, which is spanning over the entire span. It is in fact much bigger than the span itself, but it does not matter the other loads on both sides, because it is directly going to the foundation. And then we have the UDL, which is at a much smaller distance than the span, which is happening for a very long span bridge and the smaller loads of a truckload. And we have seen that it's the bending moment is maximum when the uniformly distributed load is so placed that the section divides the load in the same ratio as it divides the span. It is a very important conclusion, you must remember. And then the absolute maximum bending moment and shear force, it is easy for the cantilever for both shear and bending moment, and do not forget that depending upon the relative positions of load, if you are allowed to change, suppose the vehicle can come from this side or this side, then the condition will be different. I will always place the maximum load at extreme end. So, it is not shown in the book. So, you have to just understand engineering intuitively. Now, for the shear it is easy for simple, but for bending it was somewhat difficult, and we understood that it will be the equidistant, the resultant will be equidistant from one of the loads, and we are not sure that which load we are talking about. We will try with different loads and the resultants to place them in such a way that they are equidistant between from the geometric central line, they are equally displaced the resultant and one of the load. So, it is to be also examined for a train of loads. With that, we have concluded this session, and with an example I have given you as a exercise, and then so this was a short session, that is why we have shifted something from the other session, and we have the truss under discussion. We have seen how traditionally by computation we can draw the influence line diagram for the trusses through the solution of the trusses themselves, since it moves on the floor not directly onto the truss girder, otherwise it will be subjected to bending moment. It is not, it is always subjected to the axial forces. That means the only possibility of the unit load meeting the locations of the truss are at the joints, and that is how solution of the joints and the sections give us a solution for the influence lines. And this we have done analytically by computation, and then from the Muller-Breslau principle also have given the same shape, and that is the end of the session. It is that thing I want to show you one thing. I have there are many books. I have taken it from Professor Ramanutham's book, I should mention, because he has solved a lot many problems for the students which you can see anytime, and there are such type of diagrams which are drawn. These are very useful once you understood the basics. They are not influence line diagram, they are the maximum shear and the moment with the position of different live loads. Suppose for example, there are two live loads, you are trying to examine what is the net maximum effect of shear force and bending moment. Yes, if you push it this side, once this 20 kilonewton is on the support, you have the effect of 20 kilonewton directly onto the support and effect of 10 kilonewton through the reaction, which if placed at 3 meter, the reaction here will be 10 multiplied by 7 divided by 10 multiplied 7 divided by 10. So, it is actually 7, that is what the maximum shear is 20 plus 7 27. Such type of diagrams you will find in many books. I have extracted from Ramutham's book, Professor Ramutham's book, but it is there in many books. You can see such type of formulations. Once you understood the basics, that drawing the maximum shear and moment diagrams from the profiles of envelopes of the maximum moment and shear will be very easy. I have not done that in this particular coursework because of complexity. Let us learn the basics first, the details next. Like that we can conclude this today's session, and I will look forward for your comments and questions. So, you can right now you can ask questions. We will be waiting for at least 5-10 minutes for you and then conclude the sessions today. Yes, please. So, there is no quiz after this session, that I have decided. Let us learn it fully. Tomorrow after the session ends, we will have the assignment discussions and the quiz, proctor quiz. Okay. So, let me have your comments. If you have understood well, you tell. If you have not understood something, tell me. I will discuss once again quickly and also answer all your queries quickly. And the whole tomorrow's second hour session is for you to discuss with me. Yes, please. So, let us see that I am awaiting comments and questions from you. I have restricted myself to very basic fundamental questions, and that is how a textbook should be very concise. So, that you should read much lesser to grasp the fundamental materials, and that can be different when you refer to the reference materials, no problem. There is a question from GHRC Snehal. So, the question is that for influence line diagram of truss, which book is good? You see, I have told you I have referred a few reference books which are very concise. Even if they are in detail, they are still concise. But there are for the trusses, I think many books, many books are there which actually explains it very well. I will not name a particular reference book. I have, before attending this session, I have seen at least 15 textbooks, and all are very detailed in truss influence lines. So, if you want I can give you later, but not now, because this is not to promote the book. So, I will stick to the reference book I have shown you. You can see Professor Wang's book which I have referred here. I will show you the references tomorrow, where there is a discussion about the trusses very well, which is still concise. Many other books are there which are in more detailed, and if you are solving some problems, then you can refer to us. Presently, you can first see Professor Hibler's book, which is somewhat concise, or you can switch to Professor Wang's book for intermediate structural analysis, which is giving the truss to some extent. These books I have referred. Professor Ekejen's book also, it gives some details of the trusses. The 4 books I have referred. So, among them I want to stick to them. Professor Menon also, Professor Menon, which I have found that this Hibler's book we always refer and make it a textbook in the IIT because of its conciseness. Indeterminate structural analysis by intermediate, actually it is not indeterminate, intermediate structural analysis, C.K. Wang, that is it gives to some details about the truss. Professor Menon's book is giving somewhat more detailed analysis, and obviously Professor Jain also. So, all an NPTEL course also for IIT Kharagpur, this 5. Apart from that, there are many books which are much more detailed about different kind of trusses. You can see them. All books, I have found out one thing, all books contain the influence line information in detail. Okay, then thank you very much. Have a good day. Tomorrow we will see again in the morning 10 o'clock there will be some teaching, but the next hour 11 to 12 is completely up to you to interact, as well as I will discuss about the assignments and quiz, everything. Okay, thank you very much. Thank you for staying with us. you.